Our next speaker is Clare O'Dowd from Cameco, and she'll be talking about the seismic data.
Yep. Okay, thanks everybody. So I wrote down a couple of things that some of our speakers said today. Dawn said target resolution, averaging your signal, that kind of thing. We had another comment about using data for purpose and content, thinking about that. Colin mentioned we have to go back to the source data. So these are things that I've noticed through these talks that I also am touching on. This is more specific to seismic not technical, but applications. So I thought, there's definitely a running theme through here. I apologize to anyone who watched the TGDG talk last week. This is the short version. And if you didn't, the long version touches more on physical properties, gravity inversions, that kind of stuff. So if you want more, I'd recommend looking up the Toronto Geological Discussion Group talk from last week. But for the sake of time, I'm actually going to stick to the script. So we'll try and catch things up, because anyone who knows me, I can kind of tangent quite a bit. So we'll stick to the script. Okay. So thanks for being here. Seismic applications in the Athabasca Basin have become more common in uranium exploration over the last decade. And these have been highlighted with a number of challenges, failures, and some successes. So this talk is intended to not be a technical review of these methods, but rather a discussion of the various technical challenges and the seismic techniques that we have applied in an attempt to address them within the eastern Athabasca Basin. Okay, so the Athabasca Basin, located in northern Saskatchewan, I hope everyone's got that one covered, has been the site of over 5 decades of fruitful uranium exploration. This basin is still considered to be the foremost exploration ground in the world for unconformity-related uranium deposits. The majority of seismic applications undertaken by Cameco have been located in the eastern part of the basin, near the boundary of the Wollaston-Majatic domains. The basement rocks are comprised of gently to steeply dipping metasedimentary and granitoid gneisses. These basement rocks are unconformably overlain by the Athabasca group sediments, which are dominantly quartz-arenite sandstones, which increase in thickness from less than 100 meters at the edge of the basin to well over 1.5 kilometers in the center. The majority of economic deposits are localized around the eastern edge of the basin. These deposits range in depth from near surface to over 500 meters below surface. So as exploration advances to deeper parts of the basin, there are increasing challenges related to both the exploration, targeting, and mine development requiring closer attention. So high-grade uranium deposits in the basin are typically very small when compared to other base metal deposits. And this adds to the challenge of discovery. These deposits are also not directly detectable by geophysical methods when undercover. Here we have a schematic of a typical unconformity uranium deposit cross-section. In this case, there's little to no basement offset, and the deposit is covered by approximately 750 meters of sandstone, underlain by a sequence of gently dipping metasediments, including 2 relatively small graphitic gneisses. These are the targets for the electromagnetic methods that we've heard about, and I'll get into it in a little bit more in a moment. Given the small size of these deposits, deeper penetrating geophysical techniques are being more frequently sought after to assist in solving some of the geological and geotechnical challenges associated with them. Traditional geophysical methods outlined in this table provide a framework for the approximate resolution of each method as obtained through various inversion techniques, of which the EM is considered our bread and butter. And through these methods, we infer the presence of ideal geology, alteration, and structure. 1, 2, and 3D inversions are a way of modeling these data sets to provide an image of the physical property distributions below surface. Unfortunately, due to the physical limitations of these methods, resolution decreases with increasing depth at the source, as Ken mentioned earlier. The schematic on the left provides an example of how a 50 by 50 meter inversion cell would represent the underlying geology and target area. As you can see, the deposit would fit nicely into the little red cell. So just to provide you with a frame of reference, here's the Cameco exploration office with a 50 by 50 meter square superimposed on the Google Maps image. As you can see, it covers almost the entire parking lot. The deposits we're exploring for, or delineating, may only occupy approximately 1/5 of the cube that this represents. Not to mention, we're trying to hit it from 750 meters above surface with drill rods that have an outer diameter of 77 millimeters, using geophysical methods with plus or minus 50 meter resolution. So given these geometries, I think our exploration teams are doing a remarkable job of making a discovery of any size. But how do we obtain details at greater depths outside of borehole? Seismic methods become an obvious choice for gathering more detailed information at significant depths while maintaining resolution. Unfortunately, unlike the traditional exploration methods of magnetics, gravity, electromagnetics, and DC resistivity, seismic methods have had a slower acceptance due to financial, logistical, and technical challenges inherent to data collection, local geology, relatively long turnaround times needed for data processing and interpretation. Despite these challenges, a number of seismic surveys have been undertaken by companies in the basin, and there is a growing understanding on how and when they can be applied to explore for uranium deposits and assist in mine development. The focus of seismic applications for exploration for the unconformity uranium model can be divided into 4 main target areas from which will form the outline for the remainder of this talk. Seismic methods, depending on their design parameters, have the ability to map in detail each of these individual target areas, which include glacial overburden thickness, unconformity topography, post-Athabasca structures, and potential alteration zones surrounding the deposits, all of which can greatly impact various stages of exploration and mine development strategies. So moving on, here we have 3 of the main variations of seismic applications we're going to review. Each method is focused on a different exploration feature. The first application is a passive seismic method utilizing ambient noise to map the bedrock interface. The second are various configurations of downhole seismic surveys, which are where the source can either be the same as a traditional impact source at surface or a slimline piezoelectric source in the hole. These geometries provide the ability to image both vertical and horizontal reflections. The third, more traditional surface survey, either shot in 2D or 3D, is best for imaging horizontal to subhorizontal reflections such as the unconformity. Interpretation of vertical faults and unconformity offset in this type of data are typically inferred utilizing breaks in coherent reflected horizons, something, as you will discover, is a rare occurrence in the Athabasca Basin. But before we jump into it, I want to clarify something. The seismic reflections that we're imaging are not always faults. In fact, there are a number of things that the seismic image could be showing us, including, but not limited to, faults and changes in lithology. As most of you who are familiar with seismic methods may already know, in order to have an image whatsoever, we need to have an acoustic impedance contrast between the features we're trying to resolve. This can be a result of either a change in the density, porosity, and/or the velocity, or any combination therein. There are a number of geological phenomena that can cause acoustic impedance contrast other than faults, and while mapping them may be one of the primary goals of the seismic applications of Cameco, based on our analysis of a number of data sets, more often than not what you will see is alteration or damage zones surrounding the features of interest. These may be represented by discrete reflections easily identifiable in core as a fault, to broad zones where a reflection is observed on the outer limits of a measurable velocity change, which may not be marked by a visual change in the drill core. So again, while to those of you who are familiar with the nuances of seismic may think this is a given, there is a potential for confusion around this point, particularly where the client or end user of the data may not be a geophysicist or even a geologist, but who is particularly interested in finding faults or fluid pathways. Thus, it's always a good idea to explain the caveats and manage your expectations of a survey right from the start in terms everyone can understand. So, first target, mapping of the glacial overburden thickness. The glacial overburden can vary in the Athabasca Basin, ranging from very little to over 100 meters thick. In addition, bedrock troughs exist under both topographic highs and lows. Drilling through this and drilling through significant thicknesses of overburden can be timely and costly. Thus, having a good understanding of the glacial cover in areas of exploration can be useful when trying to optimize the location of drill hole collars and minimize overburden drilling. Traditionally regarded as a nuisance by seismologists, seismic noise has been shown to be rich in information about the local subsoil and bedrock contact. Since noise is always present and exists everywhere, it acts as a convenient exploration tool to map overburden thickness. The method uses the horizontal to vertical ratio of ambient noise as a non-invasive technique that can rapidly estimate the depth to bedrock. The method assumes a strong contrast between acoustic impedance between the bedrock and overlying layer of sediments. Existing drill hole information should be used when available to calculate layer velocities. On the left, we have one of the units, which is placed on the ground and records for approximately 20 minutes. On the right, you see the results of the test survey presented as a typical example of the passive seismic profile above the geological interpretation based on drill hole information. These drill holes were used as constraints to estimate a constant velocity for the overburden. This methodology is cheap to deploy and requires minimal training for acquisition. The second feature of interest is the mapping of the unconformity topography. Deposits are typically situated at or near the unconformity, as the model name would suggest, and mapping offsets is always in the mind of the exploration geologists because offset could indicate post-Athabasca faulting, which could provide the track for fertile fluids. A detailed image of the unconformity is also useful from a geotechnical perspective, as the unconformity is considered to be a significant fluid conduit that requires mitigation during mine development and ore extraction. As a point of interest, both Cigar Lake and McArthur River mines utilize freezing techniques to deal with the amount of water flowing along the unconformity and overlying sandstones. We already heard of EXTECH this morning. This is a portion of one of the high-resolution 2D profiles collected during EXTECH IV. The interpretation, or an interpretation, was completed across the line utilizing little to no geological constraints, and it appeared to have some similarities with the P2 fault, the primary host to the McArthur River deposit, and so it was drilled. Unfortunately, the lack of understanding of the variability of reflectivity of the unconformity and the lack of geological constraints used in the interpretation resulted in an incorrect exploration model. Subsequently, the information collected in the drill holes provided a significantly different picture as displayed here, which presents the original interpretation in blue alongside the drill supported results. The drill-defined unconformity is highlighted in yellow. No unconformity offset nor significant P2 parallel structures were identified, and the region was designated as unprospective. On the upside, these drilling results provided a unique learning experience and has resulted in a better understanding of the reflectivity of the unconformity. The sonic velocity information collected in these drill holes showed that the acoustic impedance contrast between the bottom of the paleo weathering, outlined in green, and the basement rocks was stronger than that at the unconformity interface, resulting in the misinterpretation of the unconformity offset. At a similar time, an exploration-based seismic program was undertaken on the Reed Lake project. Here we have one of the 2D seismic profiles displayed with the drill-defined unconformity and C10 fault line. For the most part, the unconformity at Reed Lake is associated with a strong reflector. However, there is still strong basement reflectors that can distract the interpreter. The C10 fault can also be observed in the profile. However, the lack of coherent reflectivity in the sandstone makes the interpretation of the extent of the fault a challenge without supporting information. Again, the 3D planes displayed here are based on drilling information. So as you can see, the quality and resolution of this 2D seismic profile is higher than that of the EXTECH IV line, namely due to the survey design. Even considering the challenges in reflectivity, mapping of the unconformity is still possible. The three slices on the left are extracted in 3D space from the Millennium 3D Cube and have interpreted cross-sections from drilling results overlaid. This image displays the characteristic variations of the unconformity reflectivity surrounding the Millennium deposit. In the foreground, directly over the deposit, the unconformity is barely identifiable. This is a result of intense alteration and faulting in the area. Farther to the north, the unconformity is coincident with a strong, coherent reflective package. But moving farther north still, the strength of the reflection and the apparent polarity of the reflection has changed again. The image on the right is the unconformity horizon as interpreted from the 3D seismic cube. The circles are drill hole intersections which were used to constrain the interpretation. General geometries may still be inferred in areas without drill hole constraints. Note the complete lack of drilling on the western half of the survey area. But as discussed in the McArthur River case, the interpretations should be considered for what they are, and should be communicated thusly to avoid future debates regarding the authenticity of the entire interpretation. From here, we're going to move on to some examples of directly imaging post-Athabasca structures, which play a significant role in focusing mineralization as a form of geological trap and conduit for fluid flow, yet another source of geotechnical challenges when it comes to shaft sinking and mine development. The challenge with inferring vertical faults and offsets in the eastern Athabasca from traditional surface seismic data is the lack of coherent and extensive reflectivity in the sandstone. The sandstone units were deposited by fluvial systems, such as braided riverbeds, that meander over time, and so the reflectivity of these beds, which may be strong in areas, is very limited in lateral extent. And so as you can imagine, trying to identify post-Athabasca sandstone faults associated with mineralization can be a real challenge. Here we have another section of the same EXTECH IV seismic profile, and as you can see, the sandstone and basement contact is somewhat ambiguous, and there is a lack of coherent reflections. In general, the faults of interest to uranium exploration range in depth from 45 through 60 degrees, and underlying basement rocks, typically comprised of folded stratigraphy, have a similar geometry. While it may be argued that some processing techniques are able to pull out images of these features with some degree of detail, these faults and basement foliations are really in what some may call a blind spot of traditional seismic surveying and interpretation methods. As you can see here in this image, the P2 fault, the host structure to Cameco's flagship McArthur River mine, could be missed in the dataset without some prior information or drilling constraints. I'd like to emphasize horses for courses here. The data in the survey should be designed with the scale and target in mind. This particular survey was clearly not designed with exploration in mind. And this is where the application of borehole seismic surveying can really make a difference. At Cameco, we've experimented with a number of borehole seismic surveys, including SideScan, which utilizes a piezoelectric source imaged in the center, which is lowered into the hole below a string of geophones on the lower right. Of all the seismic methods, SideScan provides the highest resolution, but at a cost of penetration extent. In applications, we have successfully collected up to 300 meters away from the borehole and as little as 80 meters utilizing the same source and survey design. The driving factor to the extent of penetration is the local geology. In more competent rock, your signal is going to travel farther. The borehole method, which we are going to focus the remainder of this section on, is the VSP method. This utilizes the same receiver chain as the SideScan, but a surface impact source, similar to what has been used by our 2D and 3D seismic programs, shown here on the top right. To keep costs low and to keep environmental impact down, shot points are strategically scattered about the survey area to optimize expected geometries, and this method can image over 500 meters away from the borehole. Here's a slice from the 3D seismic survey over Millennium on the left, and the corresponding VSP slice over Lane on the right. The source is the same for both datasets. The only difference is the location of the receivers. In addition to the increased frequency content and resolution, which you can see from the comparison of 3D profiles against the VSP profile of the same line, borehole seismic techniques, when processed appropriately, have the ability of directly imaging vertical to subvertical features while maintaining their frequency and resolution. This is a great interest in uranium mining industry. However, VSP processing and surveying is not new and has been utilized by the oil and gas industry for years. What makes the application in hard rock difference is in the processing. The fact that the data is taken further and processed so that reflections from both directions are maintained. The innovation of the image point transform and its application to VSP processing has resulted in elevating our ability to directly image and interpret vertical structures in VSP data while retaining high frequencies. I'm not going to go into the details regarding the processing, but would strongly recommend you refer to this paper should you be interested. Holy, that's heavy. That laser pointer is really heavy, I didn't expect that. I'm going to do some weightlifting here. This paper right here. Sorry about that. I'm going to put it down. Do some weightlifting. So as I mentioned earlier, there's a challenge of mapping the unconformity, particularly where the reflectivity of the surface is masked by alteration. Whether it be from paleo weathering or more exploration relevant alteration cell is depicted here. Mapping of this kind of alteration zone can be important as it provides information that can be used to supplement geotechnical information for mine development, as well as assist in mine planning as a method of identifying ground that may potentially be a concern during development. The Millennium deposit has a very characteristic clay alteration that surrounds the mineralization. In the photograph above, you can see how intense the alteration is. All but a few crystals of the original rock have been replaced by clay, while the metamorphic texture has still been preserved. Geochemistry and drill logging were used to define the alteration zone, shown in purple in the upper image, prior to the seismic survey. This interpretation involved a lot of creative thinking, as there was little to no drill holes in the footwall or the left side of the deposit. However, as you can see, the shape is quite similar to the shape that can be outlined using the diffuse signal imaged in the 3D cube. So now we have confirmation of the extents of the alteration, additional information that can be used to guide the collection of more detailed geotechnical information. One thing I want to emphasize is that none of the geophysical techniques that I've mentioned are designed or proposed to replace geotechnical studies, but rather they are a tool for guiding further investigations. So in summary, seismic applications in the Athabasca Basin have become more common in uranium exploration over the last decade. In total, Cameco has completed 15 separate seismic surveys, some of which have been more successful than others. The application of these surveys is mainly focused on later stage exploration and geotechnical studies related to mine development located in the eastern portion of the basin. Depending on the design parameters, seismic methods have the ability to map each of the uranium exploration-specific targets in detail and provide information for engineering-related geotechnical challenges, with the caveat that Mother Nature will always have the final say. The critical piece to ensuring success of these programs, based on our experience, is not so much in the technical specifications, which are important, but it's in the management of expectations. There needs to be an understanding regarding the turnaround rate for results, which is not going to be instantaneous. In addition, clear communication as to what may be achieved and the resolutions that will be achieved at is critical, particularly when the end user is not a technical expert. And finally, sufficient additional information will always improve the accuracy of the interpretation, especially in hard rock environments, where coherent horizontal reflections are the anomaly rather than the given. I'd like to thank our JV partners, Riva, Denison, and JCU, for allowing me to show this data and acknowledge the support of Vibrametrics over our numerous collaborations. Thank you. We're back on schedule?
Yes, we are. So if anyone had any questions for Claire or any of the other speakers this morning, we have a couple minutes before lunch.
I have a question for you.
Okay, yeah.
Where you showed the passive measurement to understand the overburden thickness?
Yes.
In that image, the image that was shown, how many measurement points were there? Like very many? It's like a profile of measurement?
It's a profile, but we typically are doing them, sorry, I'll just go back to it here. We're typically doing them maybe every 25, 50 meters. So each one of these cells here would represent one station.
Nice.
I may be, is it a wrong impression? Is there, some of the texts have been mentioned there and so on. I have some of them or in my midst right now. Is there a seeming de-emphasis of geochemistry in this whole field? I mean, if you were to peruse through an index of a recent textbook, even as recent as a 2014, the word geochemistry or things related don't seem to come up as often as one might expect. Is it because geochemistry seems to be limited to very surface sorts of things, or what? Or am I wrong?
If I may tackle that. That's one of my bread and butters is working with geochemistry. An example, and I'm going to refer to this when I come back to talk about it this afternoon. Part of the reason I went back to looking at radiometrics was because of some results from geochemical observations made part of the TGI 4 program with the Geological Survey of Canada. So Eric Potter and I did a bunch of work where we compiled a bunch of data from the Athabasca Basin, which was originally, in some cases, collected by Colin Card and the group, as well as some Ramaker's surface samples. We basically compiled this huge data set, which I think is sitting around 40,000 records now, that's now available through the Saskatchewan survey. I think you guys are handling it now.
It's on our website.
And I ended up modeling a bunch of that. And so I'm going to show a bit of that later, because it gives the justification for doing the radiometrics. But it actually shows some very significant geochemical signatures for mineralization that extend to surface. So there's a need to change some things as far as how we use geochemistry, but geochemistry has taken a back seat over the past 20 years or so to geophysics in some ways. And that was one of my sort of near and dear to my heart, is to try and tackle some of those.
And you know, there have been some other things too. Just I wanted to say, like Paul Ramaker's is the principal component analysis, and it's really tying the geochemistry back to mineralogy. And we've talked about the same thing for geophysical surveys. Can we explain things with the primary mineralogy and samples? And so it is being done, but yeah, geophysics has always been. Sorry, Dave.
Claire, I'm going to toot your horn in harness on that question. I think where we're at now with a lot of geochemistry from exploration is trying to match geochemistry to geophysics.
Yeah.
For instance, we do a lot of resistivity. Ken touched on that. We don't do, we only represent one part of that survey, and that's the DC resistivity, the resistivity factor. But we as geologists want to understand, is that alteration, or is that just fluids in the rock? What is that resistivity signature? So people at Clare and Garnet have done a lot of work, or their people have done work on looking at the clay chemistry and looking at resistivity responses and seeing if they can match that. This morning I asked the question about remnants. Clare has also done a lot of work on magnetic susceptibility. And I think one of the things, Colin, we have to clarify for the speakers is magnetics is not about magnetite only or ilmenite.
No, it's
all the minerals.
That's right.
The mag sus values of everything. So Claire's done a lot of work on looking at mag sus values, matching it to our magnetics. Hence we got the problem with remnants we discovered. There's other studies, but really to answer your question, we're trying to take geochemistry now and match it to geophysics and better understand our geophysics. Those are just two examples of what we're doing.
I almost want to build on that. I think, especially in this downturn, we're seeing a lot more presentations done by consultants and contractors, and so maybe the geochemistry that's being done isn't just isn't being talked about or being published as much because of the economic times we're in as well. Might be.
At the back, Larry?
This is a little more specific to what Claire's talking. You see a phase shift or polarity change in the unconformity between your sections that you show at Millennium. Is there a geological reason behind this, and then the second part of it, what happens in between?
It can get rather confusing when you don't have the drill hole information to get the in-between answer. But yeah, there is, some of it does have to do with the underlying lithologies. There is, like the chalcopelites are a lot more reflective than some of the other units. So it's a combination of your underlying lithology, your paleoweathering, your alteration zones surrounding it, and what's happening in your sandstone above it. Because again, it's really, you're measuring that contrast. So if you don't have a sharp contrast, it doesn't matter what your lithologies are, you're not going to see it. So yeah, it's definitely a little bit more complicated than just one thing, but it does tie back to a lot of the underlying geology. One interesting thing, even in the EXTECH, notice that you get much better reflectivity over your quartzites and even in your sandstones. And I don't know if that has anything to do with silicification above the sandstone or the lack of alteration over the quartzites. But certainly, if you look back at the EXTECHs, you're getting better reflectivity over your non-politic units as well. Jonathan?
Another question for Claire. Static correction, you didn't mention much about that, but I imagine it would be a real challenge in this environment. Are you using the Trimino data for that?
Are we using what data?
Any of the Trimino data?
No. For the Trimino stuff, that's the passive seismic units that we showed here. we've only just started using those in the last 2 years. The Millennium survey was done in 2007. But certainly the static corrections were a huge ordeal. They were done 3 different times by a university group in the University of Uppsala. So definitely the first pass gave us a good image, but the second pass where they did the really detailed refraction statics, it really improved the image significantly. So it's not trivial, and certainly anyone planning a seismic survey on that scale needs to take into consideration that that is not going to be processed once before you get a final answer.
Clark, maybe you can speak to what we're doing with GPR and how we're looking at our passive seismic results and now with GPR, because that overburden is so critical for you folks in terms of modeling our magnetics and our gravity. You need to know that overburden.
Exactly. So we are using the passive seismic data. You can use it for also taking some of that overburden, stripping out while you're doing your gravity inversions and whatnot. As Dave mentioned, we've done some GPR through the Seismic Footprints has done some, and we've also done some internally in combination with the passive seismic. And what's interesting is at times when everything's perfect, they seem to align. But what happens is where you have because the GPR, looking at your dielectric constant versus your impedance contrast, they are imaging 2 different things. So over, say, an example, a fault or something like that, your passive seismic starts to break down and it'll pick something maybe deeper that's got more of an impedance contrast, whereas your GPR may still map your map your bedrock overburden contact. So they are useful in combination. Certainly the GPR, the newer technologies and processing techniques we're seeing through the water table, and you're getting a lot more detail that you can pull out of your overburden. Is that where you're going?
Discussing various approaches to exploration and so on this morning, the issue of moisture, water, rain, etc., seem to come up regularly. Now, what about working over permafrost, muskeg? Is there a ubiquitous problem in this area, or can you assume that this overburden, this material, is generally homogeneous, and therefore you can just cancel it out in terms of your data preparation and so on?
I'd say the answer varies depending on the geophysical technique you're looking at. Don, do you want to comment on radiometrics?
Well, again, any kind of water content is going to reduce the signal. It's not going to kill it entirely, but it's going to reduce it, so you would have to take that into account. So if you have areas that have higher permafrost, like thicker permafrost than other areas, that may affect it. But again, you're going to get variations based on the actual native material. So there's all these little variables that happen you have to account for. That might be one that you have to include in your assessments when trying to interpret these. So permafrost could be.
Garnet?
Yeah, there was a great paper by Ken Hasegawa in 1993 working up in the Teton Basin regarding permafrost and the variations that result in physical property variations that you can associate with that. And I'd recommend reviewing that paper.
No, I get one.
I
You got 3.
I had one for you.
But you're paying. I just wanted to mention that Francis talked about the gravity. We had this project internally where we had access to some of these early stage Falcon surveys. And up in the Helmer area, we got some data that Carl Schiemann provided or helped us with. But one of the things we found in that data set was we actually seemed to model in the sandstone a very large, like 0.2 excess mass feature sitting in the sandstone. And I remember showing it to some people at the time, and they said, yeah, but where's the conductor? I mean, even if we were mapping the hypothetical alteration zone, I'm not saying we were, but I mean, we did parametric modeling, and it was one of those things, unless you really look hard into the dark closet and you don't see it, it's not like mag and a lot of the stuff Francis showed coming out of the basement. It's actually changes that are pretty subtle. When you look at gravity, it doesn't really respond in the same way that if you had a big like mafic sill, you could model that up pretty easily, and you could say, gosh darn, there's something sitting in there in the sandstone. The density variations are much more sublime. And unless you do some sort of formalistic parametric modeling, you don't see them. And I don't think a lot of that data has really been interrogated that way. We just sort of think, nothing's happening in the sandstone, let's just go find an image of the basement. But there are things happening. And I don't know what that feature was, but when people say, well, there's no conductor, it's like, well, I thought you said you had a model that didn't require a conductor. Oh, no, we were just kidding. Anyway, so we did.
Oh, sorry, Dave.
Yeah, so hi, I'm Jake. I'm quite new to basically the Athabasca Basin, and I spent most of my career basically just started doing porphyry deposits. I finished my PhD there, and now I'm working on these types of deposits. And I've started looking at all the assessment reports, and it seems like there's a wealth of information in the 70s and 80s that was collected, and it seems to me like it's just been left on the shelf. And we've done drilling, and we've done like a lot of other work since then. Should we kind of go back to those surveys and incorporate like our drilling and things like that onto those old data sets and try and think of them in a new way? I mean, has that been done?
I'll maybe toss this over to Garnet, because I think his talk this afternoon is going to kind of touch on that a little bit.
Yeah, you're right. I'm going to talk about this because I'm going to do a case study on the lake, which exploration started there in the late 60s. And there's a lot of great work that has been done, particularly in the 80s, that nobody references, nobody goes back to, nobody knows from. Lessons learned. Don't forget about the exposure. There's lots of great work, and yes, I'm referring to the eastern Athabasca Basin, but there's been a lot of great work done historically that's not been revisited. Some of the data, and I'll get into it in my talk, some of the data is worth overreviewing, yes, some isn't. So
it's quite easy to get access to that data and like reprocess it, new algorithms and things like that.
And another factor too, and again, we have a lot different capabilities now than we did, even 10 years ago. Geophysics has advanced through the advanced computer technology, let's face it. So, yeah, there's a lot of different tools that we should be doing.
One of the problems with the assessment files, the older ones, is there was no incentive for the companies to submit the source data until relatively recently. So in a lot of cases, the files contain an interpretation of the data or images of the data, but we do not have the actual primary data, or the primary data is not easily capturable from a scanned document, because these were all paper documents. And so that's where your biggest issue is with acquiring the data. You'll see an interpretation of it, but you don't have the source information. So Omid would be the guy to talk to about what you can actually get. He searches through the files for usable data. So if you want to talk to him about that, he would be the guy.
Dave?
Actually, that question was my preamble. I wanted to thank Ken first of all, because you mentioned, Ken, that old data doesn't mean there is no value in it.
Right.
That's what that Jake, I believe, mentioned. And because I often hear our young geophysicists always saying, I need a new survey, I need new data. So I looked at Clare, not that you guys are old, Clare and Garnet, but I looked at them and said, do we really need an old survey, a new survey, because we already have data covering this area. So the youngsters seem to always want the new survey. So I'm going to ask you, Ken, about, you talked about all the new airborne EM surveys and the variants of them. ZTEM, for instance. Can I pick a drill target off of ZTEM? I hear debate sometimes that you can pick targets off of these airborne surveys. You show Canalaska's ZTEM coverage. Could I pick a drill hole off of that kind of coverage?
I will hedge the bet and say you'll see some stuff from Garrett this afternoon that's down to the targeting scale. Now, whether what you see, if you saw it without the knowledge, there's a deposit there, would trigger an incentive to drill it, where's the geological context? There had to be some other information, but there's certainly something going on with the mineralization that shows up in the ZTEM survey. Where it's actually, I think, more relevant though, is this whole issue about where do you go look next? Because to me, a lot of what we have is, I liken it in some stories, I have a picture of a SWAT team going into a house. They are extremely effective to say, okay, you go into that house, and it doesn't matter whether there's a meth head in that house or an old lady. In 5 seconds after they enter the door, whoever's in there is going to be on the floor tied up in a gunny sack. They do not think, once they go in and do the targeting exercise, we need better intel where in the block to actually look to go into that house. And I think the ZTEM, when you look at those images, it's not a half-bad proxy for MT. And I will mention this afternoon, like in Australia, they are starting blanket programs of MT as part of a geoscience infrastructure for the whole bloody country. Just MAG alone, boys and girls, isn't going to cut it anymore. We need to add some more to the picture, and I think the ZTEM has the potential to provide
And
that.
I think Garnet will speak to that. We use ZTEM as a greenfields tool, really.
Right.
Coupled with our magnetics or ZTEM, that's our starting point. That creates that map, that picture.
Yeah.
But we still run across debates in joint venture meetings. Can we target off the airborne, or do we need to spend money on ground profiles first? You don't think, it sounds like you're telling me most of the airborne surveys still probably aren't quite there for drill targeting. ZTEM, things like ZTEM are great for that greenfields.
One of the things that it came out a couple of weeks ago was that we were talking about, we had a panel on exploration process. And I said one of the things we lacked are I think call them bookends. We focus on the middle part, but the bookends to me are defining the problem at the first and deciding the tools, and the back end is to document whether these have worked or not. What you do at the front end, people often regard as proprietary. What you do at the back end, you don't do because it's embarrassing, because most of the time they haven't succeeded. So the books just fall down each time, and you put them back up and you say, well, why don't we get better? Well, we're not really making a process out of it. We're focusing on the middle bit.
I'd say we're bookending. In the middle, but the books are all falling over on the other.
The books are great, but until we actually, to answer your question, it requires the nuts and bolts of how, we did a deep basin program. The guys have gone to Wyoming, no surprise there. 14,000 line kilometers of airborne EM. Then they did a ZTEM. Then they did Titan. And they had anomalies in all 3 surveys, but they didn't overlap. So what they drilled in the middle. They went to almost a kilometer, and they didn't even hit the basement. So what would you curse the geophysics for being so misleading? And it wasn't a geophysical failure, it was a lack of definitive information to make a good exploration decision. But a desire on the investor's part to say, well, before you bugger off, because you spent the $3 million, drill one hole.
Well, this is my bugaboo. It's all about data collection, more data, more data, more data. People are thinking, well,
Maybe they should have run with one survey, done one ground survey over it, and they hadn't gotten anything. Could they walk away? Could they walk away? If they can't, then you're probably not going to make a good decision. Lunch.
Maybe you have one more? Or?
Yeah, this might be a quick one. I'm just wondering for Ken, you talked about airborne being pretty broad-based and then the ground survey. What about drone technology? What's happening in that area and what can you say?
Good things with MAG. It's a payload capacity currently and cost benefit. Now, the Chinese and the Americans and probably the Russians have drones that could carry the weights of geophysical platforms, but they're so expensive. Like the American drones that fly around have 3 qualified pilots flying them. This is not going to be cost effective in our business. So
potentially in the future, maybe.
then it gets to size and issues of operational cost. A colleague of mine who works in the survey industry, some years ago I asked him about this, because the drones were starting to come out at that point. And he looked at me, and I reminded him of this statement a couple of weeks ago, and I said, do you remember you told me? He said, the pilots don't cost that much? And he laughed, and he said, yes, that's still the case. that if you're all your stuff, all your airplane and all your sensors cost just as much, is it really that beneficial not to have a pilot actually in the plane? Because you still have to have, these are not autonomous drones in the sense of what's currently available. They're being controlled by people on the ground. And you've got line of sight issues, you've got a number of quasi-security and operational things that make it. I've seen some decent mag data over very localized spots, and it seems it's competitive with detailed ground magnetics. Spectrometry is emerging, but it's, as Don said, it gets to be the sensor package. If you can only carry around a sensor this big, your statistics aren't going to be as good as if you can carry one that's, 2 by 2 by 2 liters or much bigger.
Lunchtime.
Yeah.
Yay!